All right, everybody, here's a video about net ionic equations and solubility. All right, let's get started. Most of the reactions that we see between chemicals take place in an aqueous environment. That means that the chemicals are all dissolved into water. And we're talking about ionic compounds here that go through these net ionic equations. And so dissolved is probably not the right word. Really, the word that we want here is dissociated. And dissociated just means that water has sort of worked its way into the compound and pulled the ions apart. And so floating around in the solutions are just the ions. All right, so here is an equation in which this kind of stuff happens. So when we work in an aqueous environment, we are going to use another symbol that you haven't probably seen so far. And so Ki, this is actually a solid compound that gets dissociated, dissolved into water, and we put a little AQ here, and that just tells you that it's the potassium ions are separated from the iodide ions, and they're floating around in solution separately. The same thing is true for lead to nitrate, is also an aqueous compound. And what pops out of here and after this double replacement reaction takes place is potassium nitrate and lead to iodide. The potassium nitrate stays in its aqueous form, but interestingly, the lead iodide, this will not be aqueous anymore. This turns into a solid compound. And so this is a good time to talk about the solubility table. And this is what we have in the classroom for you guys to use to determine what ionic compounds will and will not dissociate into water. So this column over here on the left, well, there's really two columns. There's the soluble compounds and the insoluble compounds. So these soluble compounds, these are the compounds that get the little AQ tag on it. And the insoluble, that means that they are solid. And so some people make the mistake of thinking that the S stands for soluble, but it actually stands for solid and insoluble. So the way that you use this table is to basically look at, it's easy to look at the back end of the compound and then the front end to determine if something is soluble or not. So for example, here we see that down here, halides, these are things like chlorine, bromine, and iodide. Those things typically like to be soluble. They are readily dissociate in water, except, and that's where this word exceptions comes in, except when combined with silver, lead, or mercury ions. And so if you have a compound that's like silver chloride, that will not be soluble. It's an exception to the soluble side here. Okay. The other side is for the insoluble compounds. And so carbonates, for example. Carbonates don't like to be dissociated. They typically form insoluble compounds, except when they're bonded to group 1 ions or ammonium. And so if you had something like copper carbonate, then it would be insoluble, but if you have something like lithium carbonate, it is soluble. So that's how this exceptions column works here. And it turns out that really the group 1 ions, they make things that don't want to be soluble very, very soluble. So anytime you see sodium, lithium, potassium, and so on, you can assume that that compound is probably going to be soluble. And the other easy rule of thumb is that nitrates, which we work with a lot, nitrates are always soluble. So any compound, there are no exceptions. So any compound, even some of these more infamously solid state things like silver, lead, and mercury, even them attached to nitrate, they're still aqueous. So anyway, we'll get lots of practice using this table. But with this compound here, lead to iodide, we know that's a solid by using this table. So here we find the iodide, right, which is typically a soluble compound actually, but when it's combined with lead, then it's insoluble and we would tag it with a solid. So that's how that works. So really, when we put these aqueous chemicals together, what we're really looking at is something like this. So I hope the color comes through on this okay. So what we've done here is put solid potassium iodide into water, and that breaks those ions apart. So I've got orange and blue dots here. Let's say that the orange represents the potassium and the blue represents the iodine. Okay. And then we've got lead 2 nitrate, which is also soluble, and we're going to have the purple represent the lead, and the green is going to represent the nitrate. Okay, so when we pour in, and you can see that all the ions here are separate from each other, and they're just kind of floating around in solution. And when we put them all in the same vessel, they're able to interact with each other and hopefully find their bonding partner. And what happens is that the resulting product ends up looking like this. And the potassium and the nitrate ions, they actually stay in solution. That's what this is up here. So your potassium nitrate in aqueous solution, that means that the potassium and the nitrates are still floating around separate from each other. And we still call it a product because that's how it would work in a double replacement. But the real interesting one that happens is down here, where the purple dot, the lead, is hooked up with the blue dot, the iodine. And so here, when we have these things, they actually do chemically bond, and they come out of solution as a solid. It's actually a really bright yellow solid. And it's really pretty. That's why we have the PbI2 as a solid compound. Now, what that allows us to do is write this series of equations, and you're going to be asked to do that too. So here's the first thing you'll have to do is write a total ionic equation. And to begin with, you have to have a balanced chemical equation to do this. So you'll have an equation that you have to balance prior to getting into this stuff. And what they are is really just all of the ions are listed separately if they are dissociated in water. So soluble compounds, we break apart into their ions, and that ends up looking like this. These actually take quite a bit of space to write, so give yourself some room when you do these because you have lots of ions to account for. So this is actually the total ionic equation for the equation that we talked about earlier, this guy here. So all I've done here is basically separate the potassium, the iodine, the lead, and the nitrate into their individual ions, and that you can see here. So we've got the 2K plus 1. That means because of the balanced chemical equation, we had 2 potassiums, and then that 2 is also relevant to the I with the 2I. See how that works? So we tag it with the oxidation state and with the aqueous symbol. The other compound, if you remember, was lead 2 nitrate, and the formula for that was PbNO3 which means we have 1 lead ion and 2 nitrate ions, and that's how you write this. A single lead ion with its oxidation state plus 2, and then 2 nitrate ions. And so you can see that when you count these things up, you actually use the subscript kind of like a coefficient in a total ionic equation. Okay, so these things, these 4 ions are floating around in solution. That's this cup of stuff right here. And then on the product side, we have the things that remain soluble, like the potassium nitrate. We would look at the solubility table and determine, based on it being a nitrate compound, that potassium nitrate remains in solution and dissolved. So the 2 KNO3, that's 2 potassium ions and 2 nitrate ions, and there they are. And where the real chemistry has happened, though, is to produce this lead 2 iodide solid. And so in a total ionic equation, if you end up with a solid compound, you don't break it up into its ions. That's only for aqueous chemicals. All right, so that's all of the stuff put together, and this is the interesting bit here, which you write in what's called a net ionic equation. So in an equation like this, you just leave out the things that don't change from reactant to product. So you can see based on the total ionic equation that we have 2K plus 1, and then we also have the same 2K plus 1 over here. So that just tells you that there's no real change to those ions. And the same is going to be true with our nitrates. The nitrate doesn't really change from reactant to product. So when you write your net ionic equation, you just leave those things out and you include the only thing that's the real chemistry taking place. Yeah, so net ionic equation only shows the real chemistry, and here it is. This is the same total ionic equation minus the potassium and the nitrate ions. Not that they don't exist, it's just that they don't really matter in this equation because they don't really do anything. And so we call them spectator ions. They're just the ones that just kind of hang out and they don't change, they're just there to watch, I guess. And so the spectator ions that you would list in that equation are potassium and nitrate. Okay, so that's how net ionic equations and solubility work.